And so we can start?
Yeah.
All right, everyone. So I'd like to introduce Steve Simpson, who will be speaking, opening the panel discussion with his. So thank you, Steve.
Hello, everybody. I'm glad to be here, and I didn't even know that Carl and Damir were working on this book. This is great, and I'm just delighted to hear that. I haven't been doing very much reverse mathematics in the last few years. I'm on another project. I'm writing a book on degrees of unsolvability, believe it or not. Everybody can hear me, right?
Yes.
Okay. Okay. But I have some comments about. I want to focus mainly in this short presentation here about what I want to focus on reductionist programs. That is finitistic reduction, or Hilbert's program, that is, and the other reductionist program is predicativistic reduction. So there's a theorem can be provable. A theorem can be not finitistic, not even in its statement, or not finitistic in its proof, but it can be finitistically reducible, and a theorem can be also predicative or not. But even if it's not predicative, it can be predicatively reducible, predicativistically reducible, if that's a word. So let me get into this. Foundations of mathematics. Okay, the logical structure of mathematics. But I want to also express my delight that this conference is about the philosophy behind reverse mathematics. So logic here is to be interpreted broadly. When I say the logical structure of mathematics, logic is to be interpreted broadly, that is philosophically. So it includes questions about what exists, how do we know it exists, what is our means of organizing that knowledge, and so on. So it's philosophic. It's philosophical logic as well as symbolic logic. And by the way, I'm also very happy that the Association for Symbolic Logic has philosophers in it. There's a whole sort of division of the Association for Symbolic Logic. Many philosophers belong to it, and there's a journal. The review, I think, is mostly philosophy, symbolic philosophers interested in symbolic logic. But I'm very happy about that. But logic is to be interpreted broadly. Now, many questions in foundations of mathematics arise from the concept of infinity. So what is, so this goes back to Aristotle, what is infinity? In what sense do infinite sets exist, or infinite objects exist? Or, what's the deal with infinity? So I'm going to mention three foundational doctrines: finitism, predicativism, and impredicativism. These isms, I think Walter Dean is going to have more to say about that. So I'm going to simplify it very much, but here's my takeaway. Here's the simple explanation of what finitism is. It says that the natural numbers system, or similar infinite sets, exist only as a potential infinity. We don't really have a complete set of natural numbers as a completed totality. We have it only as a potential infinity. In other words, you can start enumerating 1, 2, 3, 4, etc., ... but we never get to the end of that process. and this so this is a standpoint that the natural number doesn't the natural numbers. So you have to ask, does the natural numbers exist as a completed totality? And finitism says no, it doesn't exist as a completed totality, as an actual infinity. Predicativism, on the other hand, says that the natural numbers exist as an actual infinity. So we can both enumerate the numbers and get to the end of the process, and there's a completed totality called the natural numbers. These are philosophical positions. And impredicativism, I'm just giving it a name, says that not only the natural numbers, but also many other actual infinities exist, such as in set theory, the power set of the natural numbers, the power set of the power set, etc. And we can formalize these doctrines using these philosophical doctrines using various axiomatic systems. All right, so reverse mathematics is foundationally inspired research which focuses on the axioms needed to prove specific theorems in core mathematical subjects. So what axioms are needed? That the axiomatic structure of any science, including mathematics, is a philosophical issue, but in mathematics, of course it's illuminated by mathematical reasoning, and there's even the whole subject of mathematical logic to illuminate that. So what do I mean by core mathematical subjects? I basically mean anything in mathematics that's taught in a math department except mathematical logic. So analysis, algebra, geometry, topology, differential equations, combinatorics. These are all core mathematical subjects. I just want to distinguish them from mathematical logic, which is sort of half, oriented towards in a different way towards philosophy, but also a mathematical subject in its own right, of course. So anyway, reverse mathematicians, that is, mathematicians who do reverse mathematics, have uncovered definitive answers to many questions of this type. What axioms are needed? And these results have specific implications for philosophical programs such as finitism, predicatism, and impredicativism, and as I shall talk about, finitistic reduction and predicativistic reduction. So I've already said what finitism and predicatism are. The natural numbers exist as a completed totality or not. That say they don't exist is finitism, say they do exist, that's predicatism. Reverse mathematics takes place in the Gödel hierarchy. The hierarchy consists of formal systems. I'm giving a narrow view of reverse mathematics here, not emphasizing the role of computability, although I'm well aware that it's a lot of the research is inspired and motivated by computability. So the hierarchy consists of formal systems. The Gödel hierarchy consists of formal systems. The proofs are formalized in definitional extensions of these systems, and especially important are subsystems of second order arithmetic. And 5 particular subsystems have played a large role: RCA0, WKL0, ACA0, ATR0, Pi11, CA0. These are known as the Big Five. And I didn't name them the Big Five, but they correspond to chapters 2 through 6 of my book. Chapter 1 is an introduction. So, okay. So here's the Gödel hierarchy. This is a hierarchy of formal systems. It goes all the way up to huge cardinal numbers and all the way down to bounded arithmetic and below. I guess the weakest system would be a system where you have no axioms at all. Okay, so, but we want the axioms to be consistent. So anyway, there are the relatively weak axioms, and I'm classifying these as weak, up to weak Koenig's lemma. WKL0. Then the medium systems, you know, above that, above weak, but all the way up to the top of second order arithmetic, and then the strong systems like simple type theory, set theory with large cardinal axioms. Okay. And by the way, I can't see myself on the screen for some reason.
We can
Am
see
I
you.
here? Oh, there I am. Okay. Yeah. Okay. So the reverse mathematical perspective on all this is that the weak systems are connected somehow with finitism, and that's the weak systems are PRA, RCA0, and WKL0. Those are the ones I want to emphasize. Predicatism is connected to, I don't want to say embodied, I shouldn't say that. It's connected to the systems in the medium strength area, ACA0 and ATR0, and there's a system called IR, which I'll mention. That's Pfefferman's system for predicative mathematics. And impredicatism is Pi 1 comprehension and stronger. That's definitely impredicative stuff. Let me go into finitistic reducibility and predicativistic reducibility now. So pure finitistic reasoning is embodied in primitive recursive arithmetic, PRA. That is argued very successfully, I think, in a paper by Bill Tate, 1981. Now, the systems RCA0 and WKL0 are not finitistic because they contain the natural numbers as a completed totality. You manipulate, and there are even quantifiers over infinite sets in these systems. So they are not finitistic, but they are finitistically reducible in the following sense, that they are conservative over PRA for some theorems. So RCA0 is Pi02 conservative over PRA. What this means is that every universal existential number theoretic statement that is provable in RCA is provable in PRA. And that's a result of Parsons, 1970. And then, and furthermore, WKL0 is Pi 1 conservative over RCA0. So that says every universal for statement of the form for all infinite sets X, some arithmetical conclusion holds, that's Pi 1. Anything like that you prove in WKL0 is provable in RCA0. So that's a result of Harrington, 1977. So putting that together, WKL0 is Pi02 conservative over PRA. So that means that anything you can prove in WKL0 is actually any finitistically meaningful sentence that you can prove in WKL0 is actually there in PRA already. So that's what I mean by finitistic reducibility, and that I claim that this is a realization of Hilbert's famous program, where he wanted to reduce all of mathematics to finitism, but that's impossible, of course, by Gödel's theorems. But there's a strong partial realization, as we'll see, because many mathematical theorems are provable in WKL0. So that's finitistic reducibility. Now, for the predicative reducibility, ACA0 is necessary and sufficient for basically the development of predicative analysis, as in Hermann Weill's monograph Das Continuum. And now we're in systems that are much stronger than WKL0. The first order part of ACA0 is first order Peano arithmetic, which, that goes up to epsilon 0. That's much stronger than primitive recursive arithmetic, which goes up to, but not including the Ackermann function. Now, inspired by Poincaré's and Weil's treatment of this, Pfefferman developed a formal system, IR, in 1964, which embodies, 1964 publication, which embodies the outer limits of predicative reasoning. And as he thought hard about what is the outer limits of predicativity, and that is still much stronger than ACA 0. It's even stronger. It goes up to the ordinal gamma 0 is the proof theoretic ordinal of that. Okay, that's fine, but then these systems are predicative. IR and ACA 0 are predicative. And anything you prove in them is predicative, and that's good because ACA 0 proves a lot of mathematical theorems that are not provable in WKL 0. ATR 0 is not predicative, but it is predicativistically reducible in the sense that it is pi 1 conservative over IR. And that's in a paper by Friedman, McAloon, and Simpson, 1982. So we have these reducibilities that a theorem can be not predicative, but predicatively reducible. So somehow all of the predicativistically meaningful consequences of it, such as arithmetical sentences, would be if they're provable in ATR 0, they're provable predicativistically, maybe by a much longer and more complicated proof. Okay, so that's that. So just here's a list of reverse mathematic theorems that are equivalent to reverse mathematics, provable in reverse mathematics, and in fact reverse mathematically equivalent to it. The Heine-Borel covering lemma. Well, you've all seen these lists. The maximum, every continuous real valued function has on a compact interval like the unit interval is bounded. The uniformly continuous or Riemann integral, the maximum principle, every continuous real valued function on the unit interval or any compact metric space has or attains a supremum. In other words, there are multiple versions of this theorem. They're all equivalent to WKL 0. The local existence theorem for solutions of finite systems of ordinary differential equations. That's the Peano existence theorem in differential equations. Gödel completeness theorem and Gödel compactness theorem. These are exceptions to my rule that mathematical logic is not to be included as core mathematics. All right, and here's some more theorems that are reversible to WKL 0. Theorems about prime ideals and commutative rings, algebraic closure. In analysis, you've got a real closure and real closed fields. In analysis, you've got Brouwer's fixed point theorem, Schauder's fixed point theorem in Banach spaces, and the Hahn-Banach theorem. So all of these are familiar mathematical theorems. They are taught in first-year graduate mathematics courses, and they can all be proved in WKL 0. So just to emphasize this point, finitistic reductionism means even though we can't, there are a lot of true mathematical statements which fail recursively. There are recursive counterexamples to them, but they may be provable in WKL 0, and if they are, then they are finitistically reducible. And so that's a partial realization of Hilbert's program. Okay. By the way, I want to say that the subscript zeros here are essential to these results. You have to have if you use RCA RCA without the subscript 0, without restricted induction, with unrestricted induction, that's not phynotistic anymore. That's not phynotistically reducible anymore. So you have to, Damir mentioned and Carl mentioned that they're talking about omega models there, but you can't restrict yourself to omega models. You have to consider non-standard models because these systems have restricted induction. Okay. Here's another remark on Hilbert's program of phynotistic reductionism. Not, a few years ago, Pate and Yokoyama, Ludovic Pate, Keita is in the audience here, I think. Well, I know that he's in the audience. They solved an important long-standing open problem, namely the reverse mathematical aspect of RT22, Ramsey's theorem for two colorings of pairs. And here's a statement of Ramsey's theorem for two colorings of pairs. I guess most of you are familiar with it. This is just sort of a test case for a long time for reverse mathematics, and they showed that WKL0 plus RT22 is pi03 conservative over RCA0, hence pi02 conservative over PRA. So therefore, it's phynotistically reducible. I believe it remains open. The last I heard, it was still open whether WKL0 plus RT22 is pi11 conservative over RCA0. By the way, RT22 is not provable in WKL0, but you can add it to WKL0 and it's still pi11 conservative over RCA0 and therefore pi02 conservative over PRA. So that's a great result about phynotistic reducibility. Reverse mathematics for ACA0, here's another long list of theorems that are provable in ACA0, so therefore they are predicative. They're predicatively true. And many of these theorems are the kind of theorems that you would see in Weil's monograph Das Continuum. So they're provable in ACA0 and they're reversible to ACA0. So you need ACA0 to prove them. One of them is, well, there's a lot of variants here, but there's, let me just look at these last two, Koenig's lemma for finitely branching trees and Ramsey's theorem for colorings of n to the k for any fixed k. Are reversible to ACA0. So there are lots of things that are provable in ACA0 and reversible to ACA0. So that's a good system for reverse mathematics and the reverse mathematics of predicativity. An open problem is the status of Heinemann's theorem. It's somewhere between ACA0 and a slightly stronger system, and the open problem is whether it's actually provable in ACA0. As far as I know, that's still open. Montauban and Shore have recently done a reverse mathematical study of an aspect of this problem, but they did not answer the problem, but they showed that ultrafilter methods can be they examined the reverse mathematics of ultrafilter methods in combinatorics. Okay. Now, ATR0 is this still stronger system, which is still predicativistically reducible. And here's a list of theorems that are provable there and reversible to ATR0. Any two countable well orderings are comparable, so that's a good start. I mean, that means to get a good, decent theory of countable ordinals, you need ATR0. Ohm's theorem, a perfect set theorem in analysis, Lusen's separation theorem and descriptive set theory, and determinacy, every clopen or open game is determined. Ramsey's theorem for clopen or closed two colorings of infinite sets of natural numbers. And that's a special case of the Galvin-Prickrey theorem. I think that special case is due to Nash-Williams. Podevsky-Steffens theorem, that's a theorem, that's a version of Koenig's duality theorem for bipartite graphs, lifted up to countably infinite bipartite graphs. So that's a true theorem, provable in ATR0, and therefore predicativistically reducible. And all of these statements are impredicative. They are not provable in IR. As far, according to Pfefferman's analysis of predicativity. And they, for instance, they are false in the omega model consisting of the hyperarithmetical hierarchy. The hyperarithmetical hierarchy itself is not a model of ATR0, although the intersection of all models of ATR0, all omega models, is just the hyperarithmetical hierarchy. But anyway, but this is still predicatively reducible. Here's an open problem concerning ATR0. The reverse mathematical status of Frécé's conjecture. Let me not take the time now to spell it out. Montalban, 2017, made some substantial progress on this, but it's still not known whether the problem is, to me, the big problem is Frécé's conjecture provable in ATR0 or not? I conjecture that it is, but that's not known. Okay, and then here's a few theorems that are reversible to pi11 comprehension. They are impredicative, definitely impredicative. Theorems like the determinacy for a very low level of determinacy, but stronger than open or clopen determinacy. Determinacy for the difference of two open sets. Even that amount of determinacy is impredicative. And the Galvin-Prickrey theorem for G delta sets, that's also impredicative. So, and here's some references where you can read about these things. So that's all I have to say in the formal presentation. Thank you very much.
All right, thanks, Steve. So then let's move on to Walt.